Hello guys, welcome once more to another video in our YouTube channel. So in today's video we look at the radial and transverse motion of a particle, and we are going to be solving 3 key mock examination questions. So this video is part 1, and in part 2 we continue solving 3 other mock questions, then we dive into GC questions. So for those of you who are just joining us, endeavor to subscribe to the channel, turn on your notifications so that whenever the subsequent videos will be uploaded, you'll be always be notified to come and watch. So let's get started. Okay, so we have the first mock examination question that has been displayed to us, and I'm going to read the question. So the question reads: a particle P moves with constant angular velocity omega round a curve with polar equation r equal to a into 1 minus cos theta, a greater than 0, where r, theta are the polar coordinates referred to a fixed pole O. Roman 1. Find the speed of the particle when theta is equal to pi ln 3. Roman 2. Show that if alpha is the angle that the velocity of P makes with OP, then theta is equal to 2 alpha. So I'm going to begin by giving you guys some basic recalls that you need to know about this topic. So the first thing is that whenever you see theta dot, it means d theta by dt. If you see arrow dot, it means d arrow by dt. So theta dot is equal to d theta by dt, and remember that theta is simply the angular displacement. So theta dot simply defines the change in the angular displacement, which is the angular velocity. So we always refer to it as omega. The next thing you need to note is that whenever the angular velocity is constant, then the angular acceleration is 0. That is, theta dot dot is equal to 0 because theta dot is a constant. Remember, whenever you differentiate a constant, you get 0. Theta dot dot means you should differentiate theta 2 times, that is d squared theta by dt squared, or you should differentiate theta dot 1 time, that is the derivative with respect to time, the first derivative with respect to time of d theta by dt, or the second derivative with respect to time of theta. And remember that when our first derivative with respect to time of theta is constant, then its second derivative will give you 0 because you are differentiating a constant. Like I said, whenever you see arrow dot, it means d arrow by dt, but in most cases you're not going to be giving your arrow in terms of time, okay, because you always be referred to polar coordinates, meaning arrow theta. So your arrow is always going to be a function of theta, but you always be required to look for the arrow by dt. So in such cases, you are going to use the chain rule by writing the arrow by dt as the arrow by d theta times d theta by dt. Knowing that since arrow is a function of theta, we can easily differentiate arrow with respect to theta, that is the arrow by d theta, and then d theta by dt is what we call the angular velocity, which is theta dot or omega. So at the end of the day, we have that our d arrow by dt, which is arrow dot, is equal to d arrow by d theta times theta dot. Now the first key aspect as well is what is the velocity of the particle at any time t. So the velocity of the particle at any time t can be expressed in terms of its radial component and its transverse component. So the radial component is arrow dot, and the transverse component is arrow theta dot. This e arrow here simply represents the unit vector in the radial direction, and e of theta represents the unit vector in the transverse direction. So the next thing to note is that the speed of the particle is simply the magnitude of its velocity. Remember that the speed is a scalar while the velocity is a vector. So Roman 1 is asking us to find the speed of the particle when theta is equal to pi ln 3. So these are the steps that we are going to follow. We are going to find the velocity of the particle at theta, and then we replace theta to be pi ln 3, and we find the velocity when theta is pi ln 3. Then we take the magnitude so we can get the speed when theta is pi ln 3. Now to get the velocity when theta is theta, we need to get the component of the velocity, that's the radial component of the velocity and the transverse component of the velocity. After getting it, we now express that velocity in this form, and then we proceed. So since we need the radial component and transverse component, let's come to our velocity equation and identify what the radial component and transverse components are. So the radial component is arrow dot. Okay, so we have seen that our arrow dot is equal to the arrow by d theta times omega is actually times theta dot, but since theta dot is d theta by dt, which is the angular velocity, and it was given in the equation as omega, we just replace it with omega. Be mindful of the fact that if our arrow here was defined in terms of time, then we don't need this transformation, because to get arrow dot we just differentiate arrow with respect to time. So if it is already defined in terms of time, then automatically we just differentiate it directly, but we are doing this transformation because it is defined in terms of theta. So our arrow dot is equal to the arrow by d theta times omega, and the arrow by d theta simply means we should differentiate the function arrow with respect to theta for the first time, and then we multiply it with omega, so we get arrow dot. So differentiating a into 1 minus cos theta, we differentiate 1 minus cos theta, we get sin theta, because it's actually negative of negative sin theta, which is sin theta. Our a is a constant. So at the end of the day, we get that the radial component of the velocity is a sin theta times omega. Now the transverse component of the velocity is arrow theta dot, which is arrow, which is a into 1 minus cos theta times theta dot, which is omega. Now we can now express the velocity of the particle p in terms of its radial and transverse components, as well as the unit vectors in those directions. So we have the velocity of the particle p to be its radial component times the unit vector in that direction, plus the transverse component times the unit vector in that direction. So the first step has been done. Now the next step is to find the velocity of the particle when theta is equal to pi ln 3. Then after, we now find the speed of the particle when theta is equal to pi ln 3. So when theta is equal to pi ln 3, we get that the velocity of the particle is simply a omega sine pi ln 3 plus a omega into 1 minus cos pi ln 3. Okay, so we simplify and we get that the velocity of the particle is given by this. Now, knowing fully well that the speed of the particle is the magnitude of the velocity, it means that the speed of our particle becomes the magnitude of our velocity, and the magnitude of our velocity is simply taking the square root of the sum of the squares of the radial and the transverse components of that velocity. So we take the square root of the sum of the squares of this guy here and this guy. So when we square root 3 on 2 a omega, we get this. When we square a omega on 2, we get this. When we add both of them, we simply get a squared omega squared. And since we are taking the square root and a and omega are both positive, then we can conclude that our speed is simply a omega. Alright, now the next part of the equation is asking us to show that theta is equal to 2 alpha, given that alpha is the angle that the velocity of the particle makes with OP. Okay, so the velocity of our particle, we had it previously as a omega sine theta times the unit vector in the radial direction plus a omega into 1 minus cos theta times the unit vector in the transverse direction. So the angle alpha is the angle that the velocity of this particle makes with OP. So the tangent of that angle is simply the ratio between the transverse component and the radial component. So tan alpha is simply this component divided by this component. Okay, so having that in mind, it means tan alpha is equal to a omega into 1 minus cos theta divided by a omega sine theta. The a omegas are going to cancel and we are left with 1 minus cos theta divided by sine theta. Now we are going to use the half angle identity, which says that whenever t is equal to the tangent of theta on 2, then we have that the cosine of theta is 1 minus t squared on 1 plus t squared, and the sine of theta is 2t on 1 plus t squared. So replacing cos theta with 1 minus t squared on 1 plus t squared and replacing sine theta with 2t on 1 plus t squared, we can simplify to get tan alpha to be 1 plus t squared minus 1 minus t squared, all divided by 2t. So the numerator will simplify to 2t squared and the denominator remains as 2t. 2t squared divided by 2t simply gives us t, and our t is tan theta divided by 2. So our tan alpha being equal to tan theta divided by 2, it means that our alpha is theta divided by 2. So we can multiply both sides by 2 and we get that our theta is equal to 2 alpha. We are doing this because we are in the assumption that our alpha and theta are acute angles. Alright, So we move on to the next mock examination, which is the Northwest Regional Mock 2023. It was similar to the previous mock examination that we have solved, but the questions changed. So it was the same polar equation that was given, but the two questions under that question were different from the previous. So here we have that we need to find the radial component of the acceleration of the particle q, and q moves with angular velocity omega, which is constant, and round a polar curve whose equation is given by this. So this is the representation of the acceleration of the particle q, meaning its radial component and the transverse component. So we have that our theta dot is equal to omega, like I explained earlier, and we also know that whenever our theta dot is constant, meaning omega is constant, then theta dot dot is equal to 0. Furthermore, we have that this defines the velocity of the particle. I'm still giving this because the second question is asking us to find the speed, to show that the speed is equal to this. Okay, that's why I'm still giving you guys the definition of the velocity. So and the speed is the magnitude of the velocity. Now we begin with the first part of the equation, which is asking us to find the radial component of the acceleration of our particle q. So we have seen that the radial component is simply r dot dot minus r theta dot squared. So we need to find each term here, and then we subtract. So let us begin with r dot dot. To get r dot dot, we need to get r dot first. So our r dot is simply dr by d theta times d theta by dt. We are doing this because our r was given in terms of theta. So our r dot is equal to dr by d theta times d theta by dt. We even did it previously and we got a sine theta times omega. Now what about r dot dot? R dot dot is simply d squared r by dt squared, meaning that we differentiate r 2 times with respect to time, or we differentiate r dot 1 time with respect to time. So we are going to use this transformation, and every student should note this transformation because it is very useful. R dot dot is written as dr by d theta, that's dr by d theta of dr by dt. It's supposed to be d by d theta of dr by dt, then times d theta by dt. So this r is not supposed to be there. Okay, so it means that we should differentiate dr by dt with respect to theta, and then we multiply it with d theta by dt. If you look at this keenly, you're going to see that this d theta here is going to cancel with this d theta here, and then at the end you're going to be doing d by dr. That's this numerator is going to give us d squared r, and the denominator is going to give us dt squared. So we have not changed anything. So remember that this this identity is very important, so you can copy it down. Okay, so the r dot dot is equal to, that is whenever you're given r in terms of theta, how do you find r dot dot? It is d by d theta of dr by dt, then times d theta by dt. So this means that we should differentiate our dr by dt with respect to theta, and then we multiply it with d theta by dt. So it means we should differentiate this dr by dt with respect to theta. Differentiating it with respect to theta, we get a cos theta. Then we have an omega here, okay, and this omega now multiplies with this other omega here because the theta by dt is still omega. So when you differentiate this, you just get a cos theta. Then you multiply it with, you have times omega, then times this other omega to give you omega squared. So at the end of the day, we have that our r dot dot is equal to a cos theta times omega squared. It's very important that if you're watching this video, you try to write it down so you see the simplification. Okay, so our radial component of the acceleration is equal to r dot dot minus r theta dot squared. So we have r dot dot, which is this, that is a omega squared cos theta, then minus r theta dot squared. Our theta dot is simply omega, and we need to square it. So we have a omega squared cos theta minus r omega squared. So we can fit in what r is. Our r was just equal to a into 1 minus cos theta, and then we can bring like terms together and we simplify, okay, and we get that the radial component of our acceleration is a omega squared into 2 cos theta minus 1. make sure you simplify this to arrive at this step. Okay, now the next thing to do is that we need to show that the speed of the particle cure is 2a omega sine theta divided by 2. So I would like you to pay keen attention to this proof. So first of all, we need to find the velocity. Okay, when we get the velocity, we now take the magnitude of the velocity to give us the speed, and then we use our basic knowledge of trigonometry to simplify some things. So to get a velocity like I displayed here, we need to get the radial component and the transverse component. But we had these guys already in the previous question. So I'm just going to have our velocity of cure as a omega sine theta e arrow plus a omega into 1 minus cos theta e theta. Now what is the speed? The speed is the magnitude of the velocity, which is the square root of the sum of the squares of the radial and the transverse components. The radial component is a omega sine theta. When you square it, you get a squared omega squared sine squared theta. Now this is a transverse component, a omega into 1 minus cos theta. When you square it, you get a squared omega squared into 1 minus cos squared theta. Now we clearly see that a squared omega squared is common in the two terms, and since it is leaving the square root, then the square root removes the square, so it becomes a omega. So the speed is equal to a omega times the square root of, here you're going to be left with sine squared theta. When you expand 1 minus cos theta all squared, you get 1 minus 2 cos theta plus cos squared theta. Now adding sine squared theta plus cos squared theta, we get 1, and adding it to this one here, we get 2. Then we need to subtract this 2 cos theta. So at the end of the day, we get the speed of the particle is a omega into root 2 into the square root of 2 minus 2 cos theta. Now the next thing to do is that we need to write cos theta in terms of sine squared theta divided by 2, because that is where we are heading to. Okay, so we are going to use this identity, which says that cos 2 theta is equal to 1 minus 2 sine squared theta. So this means that if I have the angle, then it also works. So it means that I have the angle here, meaning I take the angle divided by 2, I get the angle to be theta, and I take this angle divided by 2. Then from there, to get 2 minus 2 cos theta, since this is cos theta, it means 2 minus 2 cos theta becomes 2 minus all of this. Remember that 2 cos theta is 2 times this quantity here, which is 2 times 1, that is 2, minus 2 times 2 sine squared theta on 2, which is 4 sine squared theta on 2. So 2 minus 2 cos theta becomes 2 minus all of this quantity. So we have 2 minus 2 is 0, and then negative times negative becomes positive. So at the end of the day, we get that 2 minus 2 cos theta is 4 sine squared theta divided by 2. So it therefore means that the velocity of the particle, the speed of the particle cure is a omega times the square root of 4 sine squared theta divided by 2, which therefore simplifies to the square root of 4 is 2. The square root of sine squared theta on 2 is simply sine theta on 2, because theta is an acute angle. So sine theta will be positive. So it means we have proven that the speed of the particle cure is 2a omega, the sine of theta divided by 2. Okay, the last regional mark we are going to be looking at in this question is a littoral regional mark. It was divided into 3 parts, and the questions were very interesting. Okay, so pay keen attention to the strategies and the methods that I'm going to use in this particular question. So the question reads, a particle P moves in a plane with constant angular velocity omega, where that such that at any time its polar coordinate is given by r theta, such that r is equal to a into 2 minus cos theta, a greater than 0. Find the maximum speed of the particle and the value of theta for which it occurs. So we are going to begin with that before moving on to the next question. So we need to find the maximum speed of this particle, and then we find the value of theta where that maximum speed occurs. We do the same process. Okay, so we have our velocity of p is equal to this guy here, and the speed is the magnitude of the velocity. So we'll just repeat the process that we have been doing in the previous 2 questions. So our r dot is equal to this, and then it requires us to differentiate this guy with respect to theta, and we multiply it by omega, so we get this. Now this is the radial component. Now the transverse component is arrow theta dot, which is our arrow is a into 2 minus cos theta, and our theta dot is omega. Remember, we don't just choose to use omega. We are using omega because it was given in the equation that the angular velocity is omega. Okay, so now we need to get the velocity, which is the velocity of p, not q. The velocity of p becomes a omega sine theta times the unit vector in that direction plus the radial component times the unit vector in that direction. Since we need a speed, remember that this is supposed to be p and not q. So the speed, let me just try to change it so you don't get confused, because in the next question we are going to be dealing with another particle which is q. So sorry for not editing this. So the speed of the particle p, remember, is simply the magnitude of the velocity, and the magnitude of the velocity becomes the square root of the sum of the squares of the radial and the transverse components. So we have a omega sine theta all squared to give you this, and then a omega into 2 minus cos theta all squared to give you this. Now the next thing we do is that we try to simplify. Now we see that a squared omega squared is common between the two terms, so it moves out of the square root to become a omega. In the first term here, we are going to be left with sine squared theta. In the next term here, we expand 2 minus cos theta all squared. We get 4 minus 4 cos theta plus cos squared theta. Now we clearly see that sine squared theta plus cos squared theta is 1. Adding up to 4 to give us 5. Then we need to subtract our cos theta. Now we need to get we need to get the maximum speed, okay, and we now need to use our knowledge of trigonometry. So we know that cos theta is between -1 and 1, meaning that cos theta is greater or equal to -1. Cos theta being greater or equal to -1, you can multiply both sides by 4, by -4, sorry. The left hand side becomes -4 cos theta, and the right hand side becomes +4, because we are multiplying -4 with -1, and the inequality sign is going to reverse to less than or equal to, because we are multiplying by -4. The next thing is that we need to add 5 on both sides of the equation. Adding 5 to both sides of the equation, we get 5 minus 4 cos theta to be less than or equal to 5 plus 4, which is 9. We now take the square root on both sides, and we get that the square root of 5 minus 4 cos theta is less than or equal to 3. So having that our velocity, that's our speed, is equal to this, and in the previous we have the square root of 5 minus 4 cos theta less than or equal to 3. To get this guy here, we need to multiply both sides of this inequality by a omega. Since a and omega are both positive, the inequality sign will remain less than or equal to. The left hand side simply becomes our speed, and the right hand side is 3a omega. So if the speed is always less than or equal to 3a omega, it means that 3a omega is simply the maximum value of the speed, because the speed is always less than it or equal to it. Once it is equal to it, it is maximum. When it is less than it, it is just the speed. It is varying, okay? But when it is equal to it, it is maximum. Now we could also use the sense that for the square root of 5 minus 4 cos theta to be maximum, then our cos theta has to be minimum, and then we use that condition to get it, or we develop the proof as I did. Now we need to find the value of theta for which that speed is maximum, okay? So that value, like I said, for the speed to be maximum, that's for this guy here to be maximum, then this integral here has to be minimum, because it is 5 minus 4 cos theta. So for 5 minus 4 cos theta to be minimum, then cos theta has to be minimum, okay? And cos theta being minimum, it means that it is -1, because -1 is the minimum value of cos theta. If you don't want to go through that way, you just need to equate the velocity, that's the speed of the particle, to its maximum value, and you get the value of theta, because you need to get the value of theta for which it's maximum. So since we have the maximum value as 3a omega already, we can just equate that maximum value to this guy here, which is in terms of theta, and we solve for theta. So equating a omega into 5 minus 4 cos theta to be 3a omega, we see that the a omegas cancel on both sides of the equation. We can square both sides of the equation to arrive here. we subtract 5 on both sides, we divide both sides by -4, and we get that it is maximum for cos theta to be -1, which is still at our point here. If the sign here was positive, then it is going to be maximum for cos theta equal to 1. Okay, so be very careful. So it is maximum if the sign here was positive, then it will be maximum for cos theta to be equal to 1. But since the sign is negative, then it's maximum for cos theta equal to -1. Since we are we have the square root here. So cos theta equal to -1, since we need a theta coordinate, we just have theta to be equal to pi. So when theta is pi, then the speed of the particle is maximum, and that maximum value is 3a omega. Now, the B part of the equation, we are showing that the polar equation of particle Q is given by this. Now, let me read what happens in the next part of the equation. It reads, the polar coordinates r root theta of another particle Q moving in the same plane are such that at time t, the r by dt is equal to 2a sin theta, and the theta by dt is equal to 1 minus 2 cos theta all squared. The particle passes through the point A0. Then this is B and this is C. So B requires us to show that the polar equation of the curve of the particle Q is given by this, and C requires us to show that the two particles P and Q collide. P is a particle in equation A, and Q is a particle in the next part of the equation. So we have that the r by dt is equal to 2a sin theta, and the theta by dt is equal to this quantity. So paying attention to the transformation that I'm going to use. So our dr by dt, we know by chain rule it is dr by d theta times d theta by dt. This therefore means that what is in blue here is our dr by dt that was given in the equation, equal to dr by d theta, which is in dark, times d theta by dt, which is this other quantity. Now this identifies a differential equation in terms of r and theta, and it is a first order differential equation because we have dr by d theta. So we can try to separate variables and integrate to get r in terms of theta. So separating variables, we just have dr on one side, and then we can multiply both sides by d theta, and we divide by 1 minus 2 cos theta all squared. So at the end of the day, we get the r to be 2a sin theta times d theta divided by 1 minus 2 cos theta all that squared. Since we have separated variables, we can now integrate both sides. So we integrate the r and then we integrate 2a sin theta on 1 minus 2 cos theta all squared with respect to theta. Integrating the r, we just get r, and then we have to integrate this right hand side. And to integrate the right hand side, we are going to use integration by u substitution. Why? Because we have identified that if we differentiate the denominator of this integral, we are going to get a similar function in the numerator. So we are going to do a substitution which says that u is equal to just the interior of the denominator. Having u to be 1 minus 2 cos theta, we can differentiate both sides and we get du to be equal to 2 sin theta d theta. Remember that when you differentiate 2 cos theta, you get negative 2 sin theta. But since there is a negative sign here, it becomes 2 sin theta. So we see that now we clearly see that our r here is equal to a times the integral of du divided by u squared. Because our a here is a constant, okay, so we pull it out of the integral. Now we see 2 sin theta d theta is du, that is it in the numerator, and then 1 minus 2 cos theta all squared becomes u squared, because our u was 1 minus 2 cos theta. So we are going to rewrite this as a times the integral of u raised to the power negative 2 du, and then we use the fundamental theory of calculus to integrate this. Okay, how then do we integrate this? We just use the power rule. So we have a, we have u raised to the power negative 2 plus 1 divided by negative 2 plus 1, then plus a constant of integration because it is an indefinite integral. So it means that our r is equal to negative a on u plus k. But what is our a? What is our u? Sorry, our u is equal to 1 minus 2 cos theta. So annul the negative sign here, and I can just multiply this denominator by that negative sign, and I get r to be equal to a on 2 cos theta minus 1. Now we need to look for the value of the constant of integration, and we use the initial condition that says that the particle cure passes through the point A0. A0 simply represents arrow theta, where arrow is A and theta is 0. Meaning that when arrow is A, our theta is 0. Okay, so when arrow is equal to A, our theta is equal to 0. Cos theta will give you 1, and then 1 minus 1 will give you negative 1. Times this negative here gives you positive 1. So at the end of the day, we get that our k is 0 because the left hand side will be 0, will be A, and the right hand side will be A plus k. So we subtract A on both sides, and we get our A minus A to be equal to k. So in fact, our k is equal to 0. K being equal to 0 means we can conclude that the polar equation of the curve that cure passes through is A divided by 2 cos theta minus 1, because you just need to replace k with 0, and then this negative sign here multiplies the denominator, and we get 2 cos theta minus 1. Alright, now we are ending the video with showing that the two particles collide. So the first thing I want us to picture is that if these two particles collide, then at a certain value of theta, the polar equations of these two particles have the same value. Okay, meaning that they actually collide, and they collide at a particular point. Okay, and at that particular point, their arrow values are the same, as well as the theta values are the same. So we can just observe that when theta is equal to 0, then our arrow p is equal to A into 2 minus 1. Okay, because when theta is 0, this is arrow of p. We have A into 2 minus cos 0. The cos 0 is 1, so we have 2 minus 1. So our arrow p will be equal to A. What about arrow cure? When theta is 0, our arrow cure, as we found previously, is A on 2 cos 0 minus 1. In fact, we have seen that when theta is equal to 0, arrow cure is equal to A if we simplify correctly. So we have A on 2 minus 1, which is A. So this already tells us that these particles actually collide, and they collide at a point A0, meaning when theta is equal to 0, our arrow is equal to A. But let us show it. So if these two particles collide, therefore it means that arrow P is equal to arrow cure. Now arrow P being equal to arrow cure means that arrow P, which is A into 2 minus cos theta, is equal to arrow cure, which is this. Now you see that the A cancels on both sides, and then we can cross multiply. We expand the left hand side of the equation, we bring like terms together, and then we get a quadratic in terms of cos theta. We can divide all through by the negative sign, and we arrive at 2 cos square theta minus 5 cos theta plus 3 is equal to 0. We can factorize completely, that's solve a quadratic equation by factorization. We get cos theta minus 1 times 2 cos theta minus 3 on 2 equal to 0. But if I multiply two things and the result is 0, it means either of them is 0. Then clearly we see that 2 cos theta minus 3 can never be 0, because 2 cos theta minus 3 being equal to 0, it therefore means that our cos theta is 3 on 2, which is impossible. Cos theta cannot be 1.5 because the maximum value of cos theta is 1. So it means that this product is equal to 0 if cos theta minus 1 is 0. Cos theta minus 1 being equal to 0 means that theta is equal to 0, because you have cos theta will be equal to 1, and cos theta being equal to 1, it means theta is equal to 0. So at the end of the day, we have that when theta is 0, our arrow P is equal to A, okay, and our arrow cure is also equal to A when theta is equal to 0. So we can conclude that the two particles collide. Thank you guys for watching, and endeavor to subscribe to the channel and turn on your notifications, very important, so that when the next part of this radial and transverse component of transverse motion of a particle will be uploaded, you'll be notified to come and watch. Share the video with your friends and stay tuned.